Just remember, anything you say will be captured for posterity.
But a lot of it went and just sat at the bottom of the tank. And so we turned on the heating pad. It takes a while, so you should actually go and start part 2, and we'll come back and look at this in a minute again. But what we're going to look for is how this tank changes really from the bottom up as a function of time. So every 5 minutes in the lab, come over and take a look. We'll be watching it to give you a little heads up when something interesting starts to happen. The heating pad just takes quite a while for it to heat up. Are there any questions or about what you're seeing now, I guess? Layering's pretty cool, I think.
Were those 2 separate drops, or did it split into those 2 pieces?
There are 2 drops. She actually put in 3. But the 2 that he's seeing were separate.
Okay.
And so we're sort of seeing that graph that we've been seeing in class where it's like almost like a thermocline that we're seeing, right? There's this...
Yeah, so the reason that
shearing.
You are seeing the layers, which are associated with density gradients and temperature, but the reason you're seeing the layers is because there is a velocity, there's motion. And so actually I think if we wait long enough, we'll see these, the way it's zigzagging now, it'll actually reverse.
The water is sloshing in the tank, like this.
Oh, yeah.
So it's going to slowly...
And that's because it's stratified, right? These layers can uncouple themselves from everything else. If it was, completely mixed, it wouldn't be doing it like that.
But does it have velocity because of you were adding water, or is it just because
it was coming in so fast on one end, and so the denser water was coming in, and there was denser and denser water coming in, so it just kept...
So it's going to hit that wall.
Yeah.
Yep, and then bounce back.
That's so cool.
It is cool.
But where are we going to see the convection
It's
start?
slowing down though too. That's kind of fun.
So you start on the bottom, right, where it's getting heated?
Yeah, so we're heating from the bottom up, very, very slowly. You can put your hand on here and you will not notice anything. But in 5 minutes, hopefully we'll start to see some interesting effects. So if you want to go ahead and grab your fresh water and salt water. Kate, are the salt waters in the top?
Yeah,
the salt water is cloudy, the plastic. And then here's the ice. And there's the thermometers. Remember to measure the temperature before as well as the state after. And just record that in your description.
Sandy, are you with us or against us?
And remember your prediction. I think that all of you said it should melt faster in the salt water, right? Everyone decided it would melt faster in the salt water. Is that right? You think it's fresh water. Okay, so talk to your group about it and discuss what you're doing.
It's melting fast. You guys talk about
It's starting to get a little right over there.
So tell them why.
That's probably not a good idea when we need somebody.
We're starting to get a little bit right there.
He wants to play this game.
There's a little bit of convection going on over here on this end.
Oh, yeah. It's reversed.
Yep.
Okay. Okay. We have one container with fresh water. So that which ones are fresh?
You're a machine. I pull myself down.
I'm sorry. You put salt in the cooler, but I need to stay colder longer.
Are we allowed just to take one?
Yeah.
And then share it? We'll share it.
Yeah, take a temperature before and after, just for fun.
Heterogeneous solution versus pure water.
There's some convection going on in the back. There, see some? They're showing up in here.
Oh, yeah, that's actually better than I almost.
We're saying salt water.
So it takes more energy.
What do you guys think? Which one will faster?
I know, it's... Okay, yeah. You can
can see some.
So with that, you just maybe just said that was in my little head, but so with that thinking, it would take longer. I mean, it would melt faster because it doesn't really take that nature. Like the bonds would be more loose between the water. There's something
So they get into the ice.
Okay, so some of you might want to actually come through. You might want to do it not all at once because you'll want to get sort of close, but you can start to see some convection coming in off the bottom of the tank. If you want to come around, we can talk about it. Why don't your group start?
If we want to lower it, we could even put it all the way here.
So if you get down and look right at the base here, and you can actually see it in Kip's camera also, but you see sort of these tendrils and filaments coming up off of the bottom. Can you see that? So they're not uniform, but you know, a little patch of water is heating, it gets warm enough, and it becomes unstable, and then it starts to move up. So it's pretty much contained within about this distance now, I think, if I can see right. Right
Yeah.
here. And if you remember, we started with a temperature profile where it was warm and it gradually got cooler. I guess it would look like this. And so we're heating from below, we're mixing as we rise, and then it's coming up to about, in this case, an inch. Why do you think it stops there at this point, and what's going to happen?
Cools off enough.
So as it's mixing, it's cooling, and then it reaches the level where it's at the same
density.
Same density, exactly.
So does this have anything to do with why this looks a lot like the surface of the sun, with like how the
Yeah, I'm sure convection is happening on the
those
surface
crazy
of the sun
flares
as
and stuff?
well.
How like they always like.
I
kinda
don't
go
know
up
what
and down.
these are, but
Yeah.
I mean, I think a lot of things we think about happening in any fluid are also happening to some extent in the sun. Although I guess it's a plasma, so I don't.
Yeah, I don't know about this.
I think all of the electricity and magnetism stuff comes into play there as well, which is not fluids.
So these diapirs, that's what these look like to me in terms of magma.
Oh, I don't know.
Okay.
I don't know. But like, look, you can see some like these individual little filaments coming up off. Do you see that?
Mm-hmm.
And occasionally you'll see like a little parcel escape kind of the inch realm right now. But what's going to happen is we wait longer in time to this layer down here that we're warming. Is it going to stay the same?
It's going to
height?
eventually want to go higher.
Yeah.
So as we continue to warm that, it will continue to rise and mix, and eventually we'd end up with the whole water column being constant density and continuing to heat.
Mm-hmm.
No, but at a higher density, heat faster, it actually cooler.
Yeah, they're fun to watch, like individual little pieces of it. But you can come back and check it, and like when you finish over here.
All right.
But they're
Heat capacity is
so like,
versus threshold. Is less than any intuition on They're about the same, but they're
One's 4,000, one's 4,000. I can't remember which one's which.
salt.
I feel like I use 4,200, but
Alright, so freshwater I think that is 4,000.
So you for like the hydrogen bonds or whatever, or yeah, structure is going to be stirred by the fact that there's something that's not each.
3,985.
That's at 0 acidic rate.
Yeah, that's right. That's freshwater though, right?
That's at 35.
So freshwater is higher. That's it. Freshwater is 4,200 and saltwater is 4,000.
salt does not have a high heat capacity.
But it has
Can you think about it separately?
Because you can heat up sand and it holds heat. If you heat up a bunch of salt, it would melt.
I think just look at the
Okay, next.
Yeah, some other people should come look at the convective tank.
So the ice is fresh. I have a thought. And so if we're putting
Did you want to take a look? Did you want to? Sorry to interrupt your discussion. It looked good, but
It is freshwater ice, right?
yes. So Kip, you're gonna get me talking about all kinds of funny stuff on your video, so watch out.
Okay.
Okay, so you can see now from the bottom. Do you see this layer that's formed that's pretty dark? And you see it's not homogeneous. So there's these little tendrils and filaments that are coming up individually from the bottom. So as a little area heats, it rises. And actually there's some downwelling motion also, because in a fluid when something rises, it has to have, something has to replace it, and so actually get these convective cells. And so right now we're up about a little over an inch, I guess. And as we wait in time, what's going to happen to this layer?
It's gonna move upward.
Yeah, and as it heats, it rises, and as it rises, what's it's doing with the surrounding water? It's mixing up, that's right. And so we started with a profile where we had warm water on top of cold water. We're heating from below. That heated water rises and it mixes. And why is it stopped in this time at this level? What's happened at this point?
It's hit that layer of cold water.
It's not. Yeah.
It's like a boundary between.
Yeah, so initially let's say our temperature profile was just like a straight line like this, okay?
Right.
What do you think it looks like now?
It's like.
No, it's probably a straight line here and then.
Exactly. So it's well mixed here, and it's well mixed to the appropriate temperature of this layer here. So now the density in this layer.
It's not creating enough heat yet to make it past that layer.
Exactly. But as we give it more heat, it's going to rise a little bit, and it does it in these this heterogeneous way. As we convect, we mix, and create more.
So it's like coldest here. So temperature-wise, it would be like warmer to colder, and then back to warmer.
No, it doesn't get warmer. It stays cold because you've mixed. It's not perfectly well mixed, but presumably this layer is fairly well mixed. So it's warm. You're right. We should look at that's warm, and then it gets to this layer, and in here we've mixed it up.
Oh, so it's just straight.
Yeah, and so initially it would have looked something like this, and now we're cutting it off about right here. And we've mixed up all that water and added some heat there. And we'll continue to heat it. And so in 5 minutes, 10 minutes, you can come back and look and see how this layer's grown.
Thanks.
Great video. So the last group, why don't you come take a look at the tank over here? Okay, so if you look now at the bottom, we have a pretty large layer that's formed. It's about getting close to 2 inches now, I guess. And so this is all of that permanganate that was sitting on the bottom. The water that it was sitting in has been heated, and as it's heated, it's risen in the water column and it's mixed with the surrounded water. And you can actually see like these individual filaments. Do you see that? It's not a very homogeneous process, so there's parcels of water that warm relatively rapidly and raise. And when those parcels are raising, there's actually also downward motion, right? Because we can't just lift a fluid up; something has to come in and replace it. And so you get these cells of convection that form. And so initially when we started this, we had warm water sitting over cold water. So if I were to draw a temperature profile, it would have been something like this straight line, warm to cold. What do you think the temperature profile looks like now in the fluid?
Is it straightening out more?
It's straightening out. In which part of the water column? All of it?
Both. Like, in like the bottom layer and the top.
So what happens is as water warms here, you would get warmer temperatures, but then it comes up and it mixes with the surrounding fluid. And why is this layer stopped right here? Why haven't these parcels of warm fluid gone all the way to the surface?
Because it's still, now it's matching that temperature up there.
which is it's matching the density, or in this case temperature, since it's only a function of temperature. There's no salt. And so if I were to draw a profile now, I would still have warm water sitting up here over colder water, but when I got to this layer, now this is homogeneous. It's all the same temperature, so it comes straight down. And as we continue to add heat, this layer will continue to have parcels that warm, that rise, that mix, and we're going to gradually kind of increase that layer up a little bit higher. It stabilizes at its happy temperature where the density is the same, and eventually, over time, it would come up to the full size of the, what do you call this thing, the tank. Yeah, it's really neat. You can see like these instabilities that are forming,
Is the
waves.
Is the pillowed nature of that surface, like, is that really how parcels rise?
Yeah, so when, I mean, it doesn't happen homogeneously, right? There's portions of the fluid that are getting warmer, they rise, they hit that stable stratification layer, come back down, they create waves, and that type of thing.
Mm-hmm.
So you can maybe see some stuff propagating around, coming back down potentially a little bit. Occasionally you see a tendril that gets up a little higher than the others. You see all kinds of interesting things.
So if you were only heating one half of this, would you actually get like a...
Yeah, and I'll actually show you that before the class is over. We'll turn on the heating coil at the end and can watch the circulation.
I thought maybe the heating coil was broken. The heating pad was...
It's incredibly vigorous. It within like 5 seconds the whole tank gets mixed up. So it's not very effective demonstration. So you can come back maybe in 5 minutes or so and look at it at that time.
In the fresh water versus the ice in the salt water. Yeah, this guy's creating a nice little cold, pure cold fresh layer on top, right? And it's isolating itself. Really, the water coming off of it now. Yeah, it's just creeping out. Okay? Whereas this guy, the water is plunging off of there, going all the way down. So this guy gets exposed to higher volumes of water, right?
But this guy is just working in the freshwater lens.
Right? He's trapping himself in a nice little lens of relatively
I think the salt water wasn't salty enough.
fresh water on top of the salt.
Really?
And
I
so
don't know how
all
it's
the
the bottom
heat
of that one.
below this layer
Sorry.
is blocked.
No, it's okay.
It's trapped. It's not exposed down to the
Do you guys want saltier water?
To assist.
And, just moments ago, these two blocks of ice were fairly
Don't we have to do another one?
sized, right? Yeah, and now this guy's much smaller, and that guy hasn't changed protocol.
Because he's accessing all this heat, the whole volume of
Yep,
water.
yep, and this guy is blocked from it by that stratification. So this is kind of the opposite of that eroding effect that's going on over there, right? We're eroding the stratification by adding heat to the bottom. We are increasing stratification by adding freshness to the surface. And our rate of, the rate at which we're increasing the stratification is more than the rate at which
But there's more
we're
happening
destroying
here.
it.
It's so dense that it's staying up there. Now it's 14 degrees.
You have an iPhone, right?
That's got to make it even louder.
It's not bad.
This mist is low battery. Yeah. Although you're already, let me give you a zoom out view. Here's the tank. Cool. That's a really nice layer.
Jack, the only time Jack could meet this week is right after the lab. Oh, okay. So you're gonna go. I just want to clean up.
Cold water is fresh.
Like I'm gonna say
Water that comes off the ice is just fresh water. Salt water.
I told him I'd do like 15 minutes.
So that's at the bottom.
Whereas this water,
Do we want to
sinks
just
all the
carry
way
this
to the
outside
bottom.
like we did?
But isn't
As
that
it sinks down, right, other water has to go
We
out.
could, I think.
So what
It'd
you
be
do
helpful
in
if we
terms
just
of
let
like
this drain a little
the
bit.
amount of
Because it's pretty heavy the way it is and unstable.
this shows you
So much better.
so ice is melting more rapidly.
Mix up the whole thing. Yeah, you just want to light it on this.
Really?
No, somewhere.
Yeah, I just
And sorry, I should have looked at again.
So are we supposed to run it again with less salt then?
Yeah, try it again with about 4 or 5 parts fresh water to salt water.
So you can use more interactive ones for that part, so you measure one part.
Yeah, I like the way you're saying it. The way I framed it is that the ice here.
So there's some more salt water in here.
Volume of fluid. So the heat in all of this water is available to melt that ice.
Measuring how much we do.
Yeah.
So what was the first?
I think 1 to 5.
1 to 5.
So if you want to put 4 parts in there, and you think about what you do parts of 200.
It is created its own layer.
So it's less salty?
So 800
It's possible that it'll mix, right? If there's
Yeah. The stratification is isolated.
We're doing it with less. It says make it with a salt solution that is significantly weaker.
This is actually very similar to
What would be different?
in the article, where you can actually have salty water.
It would not pass through the less stratification. Salt
Compensates for that. It's still stable in density, but the competing effects of temperature and salinity aren't sort of
This is unstable though, isn't it?
No, it is stable. So it's density drops, it's stable.
This one was unstable. As the ice melts. Yeah. This one.
Can we hold it?
This is
And I mean, technically, this upper little layer is probably unstable. I mean, it would be
less salty.
So you do
Yeah.
get melt and get mixing. It's just that it all traps over there. Try one. And this was, I mean, that would.
Need less salty water.
So now you
I don't know yet.
Work on the second part?
Yeah.
Yes.
Okay.
We're crazy.
So my suggestion, yeah, don't that. My suggestion would be to use this one. You can measure 4 parts.
Sunday,
4 or 5 parts.
Saturday is 4 feet
So-
10 seconds.
That's a good size.
I want
Maybe we should do Saturday.
plug in the heating coil really quickly.
So I remember looking at it.
Why don't we come look at the layer one more time, everybody together, and I'm going to plug in the heating coil. So you can see, some of you came and looked when it was just an inch high. Now it's almost halfway up the water column, the convective layer. And so I'm going to plug in this heating coil, so now we're going to have a different situation. Instead of uniformly heating from below, we'll be heating on one side. And so someone already talked about what they thought would happen, and you'd get a circulation, so let's watch that. To death. Okay, so it's on, and you can watch what's happening on this side. See that? It's really intense convection happening. Now we have warmer water over here than we do over there. So we have less dense water, more dense water, and the height's the same. So if you were to calculate pressures, rho dH with a bigger rho, you have a higher pressure over here than you do over here. High pressure gradient, a low pressure gradient, and you get flow coming this way, rises, has to go somewhere, it comes over this way, and then it sinks. You can see it sinking over there.
Are you assuming because it's cooler there, or just because the pressure changes?
So there's a pressure change, it converges over there, and it has to sink when the water converges.
Why was the bottom right high pressure initially?